Hello and welcome back to StickmenScience. Today we're going to keep going over OChem and talk about molecular representations today. If you remember back from the last video, we talked about different types of formulas as well as resonance structures and how to represent those. And I said in the last video we'd learn how to condense our structures. So let's begin by going over different molecular representations. Here we have the molecular formula, which does not show any connectivity. So if, for example, we take the atom C6H12, we know that we have 6 carbons and we know that we have 12 hydrogens, and that's all. We could have a lot of different constitutional isomers, but constitutional isomers are going to be different structures with the same amount of atoms in the total compound. So C6H12, that's a molecular formula. We could have multiple constitutional isomers. There's different ways that we could draw the structure. One way that we could draw is by drawing the Lewis structure, which does show an accurate representation of the molecule that we're looking for, or one of the molecules that we're looking for. But it's a little impractical for larger molecules because they can be a little bit clustered and clunky. I'll save you the time and trouble, and I'll just draw out C6H12 right here and put it on the screen. And this is what C6H12 could look like. Yeah, kind of gross. There's different ways that we can trim this down and make it a little bit easier on the eye. And one way that we can do that is by making a partially condensed structure, where we don't draw all the carbon-hydrogen bonds, but instead we shorten it down to something like this. Now, the partially condensed structure is better than the Lewis structure, but we can condense this even further, making a structure known as a condensed structure, which is going to cluster all of our atoms together to only show the important functional groups and the connectivity. I'll put the partially condensed structure over here, and the condensed structure will be right below it, and look at the difference between the two. Same exact compound, same number of atoms in the whole molecule, but one of them looks a lot neater and nicer than the other. Now, all of these structures are great when we're just trying to write them out, but we could draw them and make it even more condensed, and this is going to be the organic chemistry way that we're going to do it. Like I said in the last video, we'd be going over something known as skeletal structures, which are also known as bond line structures. So, once again, I'm going to take the same molecule that we have right here, C6H12, which is going to be condensed as CH32C double bonded to CH, CH2, CH3, and I'm going to draw out via a bond line structure. So right here we have our bond line structure, and the way that we're going to read this is by looking at all of these different corners or endpoints and know that each of those is going to represent a carbon atom. And you might be asking, okay, well, where are the hydrogens if all the endpoints and the corners are carbons? Well, at each of these corners and endpoints, we're going to assume that the hydrogens are there, but we're not going to draw out the actual bonding. When we have all these carbon corners or endpoints or junctions, whatever you want to call them, wherever the two lines meet, we're going to make sure that all of our carbons have at least 4 bonds in total. This could be to different carbons, this could be to different hydrogens or other functional groups, but we're going to make sure that hydrogens are not explicit and everything else is explicit. So the only atoms that are going to be shown here in the bond line structure are going to be the carbons at every dot or junction, as well as the functional groups that we want to make explicit. So one of the rules that we have when making bond line structures is that we want to make sure that all of our heteroatoms, which are any atoms that aren't carbon or hydrogen, are going to be shown. And this also includes the hydrogen atoms that are attached to these heteroatoms. For example, if we take a carbon ring structure and we attach a hydroxyl group, which is going to be an OH, we would draw it like this with the hydrogen attached to the O. If we didn't have the hydrogen there, then you wouldn't know if this was going to be an O-, O with 2 hydrogens, so a water attached to the ring, or just OH like it is supposed to be, which is why we want to keep the hydrogens attached to any of the heteroatoms. We could attach a chlorine here, a bromine here, or any other atom that would be a functional group. We just need to make sure that we represent it in the bond line structure. The second rule when making bond line structures is that we want to remember the hybridization for each of our carbon atoms. So right here, I'm going to draw out something that's known as an alkane. In an alkane, all of the carbon atoms are going to be sp3 hybridized, which means that they're going to be tetrahedral. And if you remember back from general chemistry, tetrahedral atoms are going to have 109.5 degrees between all their atoms. So we want to draw all of our carbons that are sp3 hybridized to each other in this zigzag pattern at about a 109.5 degree angle from each other. Same thing would apply to a carbon atom that's sp2 hybridized. So in the case of this carbon atom right here between the double bonds and the 2 single bonds, we would want to make sure that there's 120 degree separation between all of these atoms, because that's the distance between the atoms in an sp2 molecule. And lastly, the same thing would follow for a carbon that's going to be triple bonded to another carbon, or any 2 molecules that are triple bonded to each other. They're going to be sp hybridized, which means that they'll have 180 degree separation between the 2 of them. Another rule for drawing out our bond line structures is going to include the concept that we can rotate around single bonds, and the direction's irrelevant. For example, if I drew this molecule right here, it's going to be exactly the same as this molecule. You might say, well, they look a little bit different. And yes, you'd be right in thinking that they look different, but all we're really doing is rotating around this bond right here, and we can do this around any sigma bonds found in our molecules. However, the same is not true for pi bonds because as we have connectivity above and below in the p orbitals, we would have to break the connectivity between the p orbitals and reform them, and that's not something that our molecule wants to do. One other rule that we have to remember is also formal charges are essential. In the last video, we talked about formal charges and how to calculate those in our molecule, and when you have a molecule that's going to be positively charged or negatively charged, you need to make sure that you represent that in your line bond structure. For example, if I take this molecule right here and compare it to this molecule right here that has a positive charge, that's not going to have two hydrogens in the center carbon. That's only going to have one hydrogen, and we need to make sure that we represent that. Now, the same thing could also be said for this molecule over here, which has a negative charge. Here, we need to make sure that we represent the lone pair on the central carbon and make sure that has a negative charge overall, which would mean that this has one hydrogen and one lone pair, giving carbon a formal charge of -1. Bottom line is, anytime you have formal charges on your molecules, you need to make sure that you represent them in the bond line structure. Now that's how we would do it with carbon atoms, and the same rules are going to follow true with heteroatoms, so any atoms that aren't carbon or hydrogens. But we need to remember heteroatoms a little bit more since formal charges are typically going to be found on these atoms instead of the carbons. So if we take this molecule right here and we make sure that one of our oxygen atoms has a negative charge while the other is neutral, this oxygen atom right here would have two lone pairs, which we don't need to draw out the lone pairs, we can infer them, but it is good practice to draw them when you're first starting out. So this oxygen at the top has two lone pairs, and we can draw those out right here. And this oxygen right here is going to be negative. We know that oxygen would have an initial formal charge of 6, and it has one bond already, so 6 minus 1 is 5, and it has overall -1s, and we would need to make sure that we have 6 electrons in those lone pairs, which means that we have 3 lone pairs surrounding this oxygen that is single bonded to the molecule. And you could just leave it O- without any of the lone pairs showing. But again, when you're first starting out, it's good practice to draw out your lone pairs. Same could be said for molecules of nitrogen like this, where this nitrogen is going to be positive, which this molecule right here is known as ammonium, and it's going to be NH4 with a positive charge on the N. We could also have a negative charge on our N right here with 2 lone pairs and 2 single bonds. And this all comes back to the formal charge rules and why you need to know them for OChem. When drawing out our bond line structures, there's one other thing that we do need to remember, and this is going to be important when we start going over chirality, which I'm not going to get into right now. Just try to keep up with me for 1 second. So sometimes when we're drawing out molecules, they're going to have different hybridizations. Like I mentioned before, some atoms can have hybridization of sp3, and they would have 109.5 degree difference between all the atoms. Well, we can't just draw our line bond structures in a zigzag pattern, because how are we going to represent a 3D structure with lines that are all in a two-dimensional plane? You can't do that. One way that chemists have learned to counter this and draw 3D structures in a two-dimensional plane is by drawing these things called wedges and dashes. For example, if we drew out a compound like this with an OH group and an H attached at this carbon right here, we would want to make sure that we represented that this carbon atom is tetrahedral and has a three-dimensional structure. One way that we could do this is by drawing the OH on a wedge, which means that the hydroxyl group is going to be coming out of the page towards us. So one way that I could represent this is by making this window pane right here with a person on one side. The wedge is going to be coming towards that person. And over here on the other side, we're going to have our hydrogen on the dash. And what the dash means is that this is going out of the plane. This hydrogen is going away from the person. So once again, if we look at the plane example of a person standing on one side of the plane, the dash is going to be going backwards into the plane away from the person. And we could switch these around where the OH is on a dash and the H is on a wedge. It doesn't necessarily matter for right now, and you're going to learn that as we get more into chirality, but for now, just understand that when we represent three-dimensional structures, we're going to be using our two-dimensional lines as well as wedges and dashes to complete the overall picture. Now, one last thing before I end this video is that we need to understand some of the different functional groups, and this is where all of the chemistry is going to happen and what separates general chemistry from organic chemistry. Right here, we have this structure that is only composed of carbons and hydrogens and only has single bonds. This is going to be known as an alkane. Now, alkanes aren't very reactive because they're made of carbons and hydrogens and they don't really have any energy difference throughout the molecule, so they're going to be relatively stable. However, if we were to introduce something like this double bond into our structure, the alkane then becomes an alkene. That ending "ene" means that you have a double bond between two carbons within a structure that only has carbons and hydrogens. If we add another bond to this, making it a triple bond, then this is going to become an alkyne. And once again, we need to remember that the alkyne, or the triple bond, will have a 180-degree separation between the two atoms, and we need to draw this when making our bond line structures. Some other functional groups that we might need to know are going to be alkyl halides, which are going to be alkanes that have any halogen attached to them. So this could be chlorine, this could be bromine, iodine, fluorine, etc. As long as it's in the halogen group, an alkyl halide can be formed and represented. Over here, we're going to have an alcohol, which is going to be the addition of a hydroxyl group. And this is going to be different than an ether, which is going to have your oxygen in the center of the molecule connecting two different alkanes together. Similar to an alcohol, we have these things called thiols, which is going to be a sulfur instead of an oxygen there. This works because oxygen and sulfur are in the same group, but different periods. And sulfur has some different properties than oxygen, but we're not going to get into that right now. And like the counterpart to ether, we're also going to have sulfides, where our sulfur is in between the two alkanes, which all these right here are single bonded or have sigma bonds, but we do also have other functional groups where we have double bonds attached to our heteroatoms. One example is ketones, which is where you have a double bonded oxygen connected to a carbon with two other carbons on either side. And these are just some structures that we will go over. You don't need to know these right now since we will be going over them a lot more, and eventually they'll become muscle memory to the point where you know them by name. Alright, that's going to be all for this video today. If you have any questions, leave them in the comments down below and I'll try to answer them as soon as I can. If you enjoyed the video, make sure that you subscribe, like, and share to continue learning and have the chance to win some special prizes coming in the near future. Once again, I want to say a big thank you to the 16 subscribers I've got right now and some of the support from the comments in the last video. I'll try to upload more regularly and make this one of my main focuses, so let me know what I can do better to improve the video and content quality. And with all that being said, thank you and have a great day.